In this video, I'll be talking about polar coordinates and rectangular coordinates and how to transition between both of them. So this whole mess that you're seeing right here on the left side of the screen is just what the polar plane looks like. Do not get scared because it's a lot easier than it seems. But let's go ahead and first talk about rectangular coordinates, what all of you guys are familiar with. So this right here is a rectangular coordinate. A simple point on, let's say, on 3, 3. All right. So this coordinate point is on 3, 3. What does this mean? 3 and 3. Well, this means that your 3 in the x direction and positive 3 in the y direction. So if we were to write this out, this distance would be 3 units, and then this distance would be 3 units. Correct? Well, what you can actually see is that you form a triangle. So all your points kind of form a triangle, right, in the rectangular plane. Now, here's the thing about this triangle. It has some relation to what you're going to be doing in the polar plane. So let's explain this. Oops, I removed the triangle. So here's the thing about polar coordinates. In Cartesian coordinates, or rectangular coordinates, you have your little pair, x and y. But in polar coordinates, you have a pair, r and theta. Alright, so you still have a pair of values, but this time the pair is r and theta. What does r mean? What does theta mean? Well, the thing about your triangle here and how it has some relation to polar coordinates is that the magnitude or the length of the hypotenuse of this triangle formed by these two coordinates is the r, which is the magnitude of your polar coordinate. That is what it's called. So the magnitude of your polar coordinate r is the length of the hypotenuse of the triangle formed by these two coordinate points. So how do you find the length of this hypotenuse? Well, you could use Pythagorean theorem, right? Since this side length is equal to 3, and since this side length is equal to 3, well, you know a and b. So a squared plus b squared square root is equal to c, correct? So we have 9 plus 9 square root, which is equal to the square root of 18. If I want to simplify this, you just get 3 square root of 2. All right. So the magnitude, let's remove this, remove this, remove this. So this guy right here is the, you know what, I should write this in yellow. This guy right here is the magnitude of your polar coordinate if I wanted to transition this guy into this guy. So we should write down, let's write down 3 square root of 2 here. All right, and now we need to write down the angle. Keep in mind, I have to erase that. Keep in mind that the actual position of your point is the same on the polar and the rectangular. So if I were to, let's say, overlay this entire guy with the polar plane, right, the coordinate point would be maybe, okay, let's make this to scale, like right here. Yes, the polar form of this point is just exactly right here. Right, it's the same thing. Okay, so the position of the point doesn't actually change. It's that our representation of the coordinate changes. So if I were to draw that, it would be somewhere around here. Yes. Okay. So now that we know that the length of this triangle, or the length of this hypotenuse, is 3 square root of 2. What about the angle, right? We have a theta. Theta usually represents angle, so hopefully you can assume that's just what we're talking about. So in order to find the angle, you need to look at the hypotenuse, and you need to see the angle it makes with the positive x-axis. So the angle it makes, so the angle this hypotenuse guy makes with the positive x-axis is what determines theta. And what does that mean? Well, it means this angle right here. So this guy is going to be the angle of your polar coordinate. So what's the angle of this? Well, in order to solve for that, we need to use inverse tangent. So inverse tangent will tell us the angle, hopefully you know what inverse tangent does by now, since polar coordinates are the end of calculus 2, but inverse tangent gives you this angle when you input the opposite over the adjacent sides. So the opposite side was 3, the adjacent side was 3 to this angle, so 3 over 3 is the input of inverse tangent. And if you want to know this, well, I can already tell you it's 45 degrees or pi over 4 radians. Now, here's the thing about this. Actually, let me double check that in my calculator. Here's the thing about this. Yeah, it is 45. You usually represent these polar coordinates in radians. So you want to use radians. You're not going to use degrees. This guy, get that out of here. We're going to use radians. So pi over 4 right here is the theta value for your polar coordinate. So what does this mean? Well, r stands for 3 square root of 2. So 3 square root of 2 should be the distance from the origin to your point, which makes sense here, right? And the angle that this line makes with the positive horizontal axis, positive x-axis, whatever you want to call it, with this axis will be your theta value. In this case, it was pi over 4, which makes sense because we actually drew this point along the pi over 4 line in the polar coordinate. This line right here represents pi over 4 radians, and, well, this line made an angle of pi over 4 radians with the positive horizontal axis. So let's do a quick little recap. How do you find your rectangular coordinate to polar coordinate? You simply need to draw a triangle, find the magnitude of the hypotenuse of this triangle, and then find the angle the hypotenuse makes with the horizontal x-axis, or positive x-axis, sorry. Now here's the thing about this. Let's undo all this. Let's show you a little more examples of a point. Okay, I need to erase this, I guess. So if I were to draw this again. Let's go ahead and do one more example and show you how to use inverse tangent properly as well, since there's a couple extra rules that you need to know when turning rectangular to polar. So arrow, 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 arrow. Now keep in mind, it's actually very helpful to learn polar coordinates. You have to use these for parametric equations, and you also have to use these if you're going to take calculus 3. Yeah, calculus 3. There's going to be a lot of integration using polar coordinates, so this is not useless. Well, maybe it is useless if you're going out for your career. Could be useful. Well, I'm not an engineer yet, but all right. Let's choose this point right here, and let's say that this point is negative 3, negative 1. Let's say that. All right. Well, we know that the length here is negative 3, and we know that the length here is negative 1. Correct? So if we form a triangle using red, form this triangle, remember the magnitude or the length of this hypotenuse is your r value for your polar coordinate. So let's go ahead and find r. Remember, all we need to use Pythagorean theorem. So it's a squared plus b squared, all square rooted. But here's the thing. A and b, we can just treat them as positive because if you square negative numbers, they will always be positive. So we have the square root of 10 here. Therefore, the square root of 10 is the magnitude or the length of the hypotenuse. Therefore, it is our r value for a polar coordinate. All right. How about our angle? Well, the angle this makes with the positive x-axis looks like this. All right? So, the angle the hypotenuse makes of your triangle with the positive x-axis is this yellow angle here. So, keep in mind, it's always from this direction, in the counterclockwise direction. It's never in the clockwise direction. You never want to measure this angle here. You always want the angle to be in the counterclockwise direction. So for example, if you hit a point here, and this is the hypotenuse of that point, you want to measure this angle like so, right? You go counterclockwise to the positive x-axis to measure the angle that your orange line or this new hypothetical orange line makes with the positive x-axis. All right, so never go clockwise, always go counterclockwise. So now we have to measure this. Well, we can actually measure this using inverse tangent again. So use inverse tangent, and inverse tangent of this angle here, so the angle of the triangle. So if you ever learn about the unit circle, you always know that if you take any triangles you want to do anything with triangles in your coordinate plane, then you want to look at the angle facing in the horizontal directions, right, for this triangle. So what I mean by this is that you don't want to make a triangle that looks like this. All right, the hypotenuse would be right, but this angle will be wrong. Right, you don't want to take this angle. You always want the triangle to face in the x directions. You also want to always look at the angles that are facing in the x direction as well. So this angle right here is what we're using as reference for our inverse tangent. Remember, inverse tangent is opposite over adjacent. So what's the opposite value of this angle? The opposite value is -1, and the adjacent value is -3. And let's look at the answer we get out of this. Well, the answer we get out of this is about 18.43 degrees. Well, why doesn't this sound right? That doesn't look very right, does it? Well, the reason why this doesn't look very right is because 18.43 degrees is this angle, no? That's 18.43 degrees. That's wrong. This is completely wrong. Here's the thing about this. When you have your coordinate point on the negative x direction, right? So if you're on quadrant 2 or quadrant 3 with your points, when you take inverse tangent, it won't give you the right output. So inverse tangent only gives you an output of -90 degrees to, what's the output? To positive 90 degrees. All right, so these are the possible outputs. Here's the thing. This angle right here is not within positive 90 or negative 90, right? This right here is negative 90. Anything past this quadrant to the left is no longer negative 90 degrees. And anything past this upper quadrant to the left is no longer positive 90 degrees. So inverse tangent only inputs or only correctly outputs the angles on this side of your coordinate plane. So what you have to do here is simply add 180. When you add 180, you will get the right angle, which is 198.43 degrees. Now, if you want this in radians, let's see. If you want this in radians, I'll show you. Well, you have to put in radians for these coordinates, but it's 0.322, approximately 0.322 radians. If you want to turn this into the right guy, you just need to simply add pi. All right, pi is equivalent to 180 degrees. Correct? So remember, previous one, we added 180 degrees in degrees. Now we're adding pi in radians. So if we add pi to this, simply adding plus pi, now you get 3.46 radians. So 3.46 radians is about right. And remember, this point right here is still in the same location. We're just representing it with different coordinates, with a different coordinate system. So this guy right here will maybe approximately be like right here about. Maybe if I give or take 1, 2, 3, right here. All right. Or yeah, this looks about more right. So this is our coordinate point. Wait, hold on. Let me double check. Okay, I was right. No need for double check. Yeah, this is about the right coordinate point. The reason why I checked this is because I don't want this point to be past 7 pi over 6. 7 pi over 6 is a larger angle, or it's a larger radian than 3.46. So I wanted this just behind 7 pi over 6. You don't want this. I didn't want this on this side of 7 pi over 6. So this right here is about our point, and we know that your magnitude is square root of 10. And the angle that this makes with the positive horizontal axis is 3.46. Now, here's the thing about this polar plane. The reason why I made sure to put this past this circle here is because each circle represents 1, a radius of 1. And I'll actually get into that right now. I'll explain how to plot on the polar plane rather than just turning rectangular to polar. Hopefully you know how to do that by now. But let's go ahead and plot on the polar plane. Let's say we had a point 3 and the radians was, the angle was pi over 3. Now keep in mind you can see this in a different form. Sometimes you might see 3 with an angle pi over 3. This simply just means the same thing as this. They both are the same thing, except that now 3 represents a magnitude. This angle guy represents pi over 3. The angle pi over 3. Alright, these two are equivalent. Left side is magnitude, right side is the angle. But in calculus 2, I think they usually represent it like this, so we're going to use this guy right here. So 3 pi over 2. How do you plot this? How do you put this on the polar plane? Well, we're going to look at 3 first. We're going to look at the 3. So remember, each ring stands for a magnitude of 1. So this ring right here, this first inner ring, represents a magnitude of 1. So if you were to plot a point on this ring right here, and this would represent a magnitude of 1. Correct? Well, if we were to plot here along this further out ring, this would represent a magnitude of 2. Now how about all the way out, this outer third ring, or this inner third ring technically? This represents a magnitude of 3. So now we are in the right spot. 3 represents the magnitude. We want to be somewhere along this ring right here. So we need to look at the angle now. What's the angle? Pi over 3. So we need to look for pi over 3. Pi over 3 is along this line right here. So we want to be along this line, and we want to be along the third ring. So where is that? Right over here. So this represents the point 3 pi over 3. All right, let's try another one. Let's try 1/23 pi over 12. All right, let's try this out. So this guy, 1/23 pi over 12. Try it out yourself. Try it out yourself. So what we can actually do is look at the first ring. Remember, the magnitude we're looking for is 1. So we want to plot this along the first ring somewhere. I already gave you the answer. Oops. But what we want is to be along this first ring and to also be along the angle 23 pi over 12. So 23 pi over 12 is along this guy. And we also want to be along the first ring. Where's the intersection point? Is this right here. So this point represents 1/23 pi over 12. Alright, let's go ahead and do the opposite now. So we want to find the polar coordinate by simply putting something random on the plane. Let's go ahead and pick this point right here. Alright, let's go ahead and tell you, or you guys do this. You guys do this. What is the polar coordinate of this point right here? Well, the polar coordinate of this point is, try it out. Well, we know that this guy's on the third ring, first ring, second ring, and third ring. Therefore, the magnitude of this point right here is 3. All right, how about the angle? Well, the angle of this point right here is along the line 7 pi over 6, right? This line right here represents 7 pi over 6. Therefore, the angle is 7 pi over 6. All right, it's not that bad, okay? One last thing I would like to cover before ending the video is turning polar coordinates into rectangular. So let's go ahead and do that. We have this point right here. And remember how to graph this. This point is on the fourth ring, therefore the magnitude is 4. And the angle is 2 pi over 3. So this right here is your polar coordinate. Oops, 2 pi over 3. How do you turn this guy into x and y coordinates? Here's the thing. It's a very simple formula. Simply r cosine theta and r sine theta. That is really all. So x is equal to r times the cosine of theta. Oh, excuse me. I just ate some. Paused the video and ate some wavy Lay's chips. So that burp tasted like that. And y is equal to r, magnitude, times sine theta, the angle. It's very simple. You can memorize this if you want, but you can also know the logic of it. I'll explain that another time. But Well, I'll explain that later in the video. Let's go ahead and do this first. X is equal to 4 cosine of 2 pi over 3. And y is equal to 4 sine of 2 pi over 3. That's really all. It's actually pretty easy. All you need to do is plug this into your calculator. So let's go ahead and do that. 4 times cosine 2 pi over 3. And 4 sine 2 pi over 3. So you have x is equal to negative 2. And y is equal to 3.46. Booyah. If we write this in your pair form, we have negative 2, 3.46. That is all. And that makes sense, right? This looks like about negative 2. And this looks like about 3.46. So that is good. Let's do this with one more point, and then I'll explain where you can get that formula from, or where this r cosine comes from. So let's pick a better color. Let's pick pink because that's fun. Let's go ahead and look at this point right here. So this point's on the 5th ring, therefore the magnitude is 5, and the angle is 11 pi over 6 radians. All right, remember, you find x by multiplying r times cosine of theta and y by r times sine of theta. All right, let's go ahead and substitute all these values. R is equal to 5, cosine of 11 pi over 6 is theta. R is equal to 5, sine of 11 pi over 6. All right, so we have x and y now. Evaluate this in the calculator. Wait, let me evaluate it. Hold on, guys. Yo, stop rushing me. Stop rushing me. Okay, so you have 4.33, negative 2.5. And our pair is 4.33 and negative 2.5. Looks about right. This guy right here is maybe 4.3. Well, it is approximately 4.33 in the positive x direction and 2.5 in the negative y direction, right? So this makes sense. But, how in the world do we get the formula? Well, let me explain. So x is equal to r cosine of theta. Let's write it down first. Y is equal to r sine of theta. Now remember, when it comes to coordinate points, there's always going to be some triangle, right? Let's draw the triangle in this case. The triangle in the case of this point right here was this right here. Now remember, the triangles always face in the x directions, left or to the right. The triangle will never face downward like this. Oops, wait. Oh my god, I can't redo it. I have to redraw the triangle. Okay. But what does cosine equal? Oh my god. Cosine of theta equals adjacent over hypotenuse, correct? So COA and sine of theta is equal to opposite over hypotenuse. Here's the thing about the hypotenuse. The hypotenuse's length is equal to r. So we can actually just replace hypotenuse with r. And what we actually get is x is equal to r times cosine of theta. And cosine of theta is equal to a over r, so we can substitute cosine of theta with a over r. And y is equal to r times sine of theta, which is equal to o over r, so we can substitute again. Look what happens. These r's actually cancel out, and we get left off with x is equal to a and y is equal to o. Here's the thing. Whenever you're referring to adjacents or opposites, you look at the angle that is facing in the x directions or the horizontal directions, and the adjacent value to this angle is actually this length or this side length of the triangle, and the opposite value is actually this side length of the triangle, right? The opposite to this angle. So what does this look like? Well, the adjacent of this triangle is your x value, and the opposite value of this triangle is the y value in order to plot your point, right? So, yeah, especially since I explained this in the beginning of the video, but yes, x is equal to the adjacent of the triangle, and y is equal to the opposite of the triangle. So, these formulas right here can just simply be derived from using this guy right over here. Very easy, very simple. But that's it for this long ass video. If you have any questions, put it in the comment section. If you found this video helpful, subscribe to me. Let me know the video. Thanks for watching.